I think this one is going to be more theoretic.
Yeah. So just to prepare you for a little shift of gears here. So I'm a mathematician at Caltech. I'm in probability. I do some pure math, and I also do things related to economics. So this is really stuff that comes from economics. It's related to the topics of this workshop because it's about social learning. This is going to be completely theoretical. And I'll tell you about a few papers that are with various subsets of these co-authors. So social learning, it could mean different things in different disciplines. I'm going to think about people, or maybe computational agents, or animals, maybe not ants, you'll see what these be pretty sophisticated agents, who learn from observing the actions of others. So we're all trying to figure out what is the right thing to do about whatever it is that's out there in the world. And I make my choices, I see you make your choices, and that reveals to me some of the information that you have, and maybe it changes what I do. So I'm learning by observing other people. What I'm not going to have is direct communication. I'm not going to tell you, oh, I did this experiment and the ants did this and that, so now I learned something. You just have to observe my choices that I'm making. And we're going to have sort of rational Bayesian agents. Everybody's going to have a complete understanding of the world, and they're going to make calculations and optimize, which is, of course, a stretch for anything happening in real life. But to me, it's kind of interesting to understand, okay, what happens in this sort of limiting case of people who are really optimizing, and what can we say that maybe even fails when people do that? And we try to do formal proofs, so that severely limits how rich the models can be, because once you put in too many moving parts, there's no hope to prove anything, so it's going to be quite stylized. Okay, so if you haven't seen this before, there's quite a literature that's 20, 30 years old by now, that comes from economics about how herds form even for rational economic agents who are trying to optimize. So these are two papers from '92 that introduce more or less the same model. Imagine that there are two, you come to a town, you come to Berkeley, you're not from here, you have to decide to go to restaurant A or restaurant B, and each person gets some kind of information about the rest, and you want to think about these as independent signals. So we're not all reading the same Yelp review. I don't know, maybe we walk by the kitchen, we each get a little whiff of what's going on in there. The model is very simple. Agents arrive one at a time. Each agent gets this sort of noisy signal about which restaurant is better and makes a decision where to go. So the first agent, depending on their signal, will choose to go to this restaurant or that restaurant. The second agent also sees what the first agent did, so they don't know exactly what the first agent's signal was. If it was strong or weak, they just know what the decision of the first agent was. They also get their own signal, but now they have two pieces of information to go by, their own signal and the action of the person who came before them. So maybe if you went to restaurant A, but I get a very strong signal that restaurant B is better, I might go to restaurant B. But what ends up happening in these models is that if I'm the 100th person to come, and everybody before me went to restaurant A, it doesn't really matter what my signal tells me anymore. I'm just going to say, okay, even if my signal is pretty strong to go to B, all these people made the other choice, I'm just going to go to restaurant A. Now, once that happens, I'm not even looking at my signal anymore. The person after me can infer that. They know that I didn't even look at my signal. They learn nothing new from me. They face the same exact choice, and then a herd forms. Right? So it's a very, very simple intuition. If everybody is doing something, there must be a good reason for them to do it. My own signal is relatively weak. I'm just going to discard my own signal and go with the herd. And this was a nice paper that sort of put this in a formal setting. Please ask any questions or okay. So this, and there's hundreds or thousands of variants of this, and I'll show you two of these 1,000 today. Okay, so I'm going to have a state which I'll call either high or low, or maybe it's restaurant A and B, but it's something that that's out there in the world. And people are going to have some in their minds, there's going to be some probability that the state is either this or that. You come to this town, maybe it's half-half that this restaurant or that restaurant is better. We're going to have discrete time. And in our model, we're going to deviate from the one that I showed you is in each time period, each person is going to get a new signal about the state. So I'm doing an experiment every time period to try to figure out what's better. So maybe the restaurant story is not so good anymore. Maybe what I'm trying to do is I have to decide some kind of lifestyle. I have to decide whether to have margarine or butter with my breakfast. So what do? I go to my lab, I do some experiment, I figure out, I get some noisy signal about what's better, and then I have breakfast and I eat margarine or butter, and then I go on Instagram and tell everybody what I had for breakfast. I don't tell everybody all the details of my experiment. People can just observe what it is that I do. Okay, and you can imagine many other settings where we're trying to figure out whether to take this action or that action. Which one is the right one depends on something out there in nature. We're not sure about it. We're all collecting information about this thing, and we're seeing what other people are doing. So, another example is a country is trying to develop some technology in a lab. They don't know whether to go in this direction or that direction. They're doing experiments. They're putting products out there. They can observe the experiments of their competitors or of other countries, but they can see which direction, what action they're taking, which direction they're going. And the question is, what happens? So this is the basic model. Okay, so let me be a little bit more formal. We're going to have the state that's either low or high, each, say, with probability 1/2. We're going to have discrete time. We're going to have some finite number of agents. So think, we have 2 agents or 7 agents. The information available to agent I at time t, I'm going to denote this by this curly f. And then each agent is going to get a signal in each time period. So one way to think about these signals, if you want to think about an example, is the following. Imagine that there's a coin, and the coin is a 40-60 coin. So all coins in the world are 40-60. We just don't know if they're 40-60 or 60-40, right? So the cents that are mint, or the quarters that are minted by the U.S. Mint, imagine that they're all not really fair coins. They're all, 51-49 coins. We don't know what it is. So what do? We stand there and we each toss it. We buy a quarter for a quarter, and we toss it. Each time it comes up heads or tails, that tells us something about whether it's say we know it's 51-49. We just don't know in which direction. So that's the binary state. Every day, each one of us tosses this coin, and every day we're going to choose an action, which is going to be our guess. Is it biased towards heads or towards tails? And we're going to exactly optimize. So we're going to calculate the probability that the state is biased towards heads, condition on all the information we know. If this probability is bigger than 1/2, then we're going to say heads. Otherwise, we're going to say tails. And what's the information that's available to us? It's my own coin tosses and all the actions, all the guesses of everybody who came before me.
But do you care about the coins of others? You want to assess your coin?
No. So the point is, so the story is, every quarter that's ever been manufactured is biased in the same way. Right? Because the head of whoever, Lincoln, or I don't know who's on that, as the nose is tilted this way or something, right? So they're all biased 51-49. All the coins are biased the same way. So when you do an experiment with your coin, it also tells me something about my coin. Does that make sense? Yeah. Okay. I have to come up with a better story. I don't know. Is this good? And people are actually doing this calculation. Now, this is a very tough calculation to make. So my guess is I don't know how to do this, but there should be a formal proof of hardness of this calculation for the theoretical computer scientists here. Because when I'm looking at your action in the 10th period, I don't know what all your coin tosses were. I can say, okay, you took this action because you saw what other people did up to that point, and maybe that tells me something about your own. Anyway, it's a very, very complicated calculation that I don't know how to reason about directly, but I do assume that people or agents or wherever it is carries out this calculation. Okay. Let's talk about a very, very simple case. So there's only one person. So what does this person do? They toss the coin every day, and then they guess if it's heads or tails. When I'm one person, it's a very simple calculation. If I had more heads than tails, and my cost says until now, I'm going to guess heads. Otherwise, I'm going to toss tails. It's a very simple exercise. This is like a classical, for one person, this is like a classical hypothesis testing setting. I just keep on doing this experiment. Under the hypothesis, I get outcomes from one distribution. Under the null hypothesis, I get outcomes from a different distribution. I do my Nyman-Pearson, whatever, and I go with whatever is best. And I can ask, what is the probability that I'm wrong at time t? Okay? And it turns out that this is classical things from like the 40s, 50s. Being wrong is that I guess incorrectly, right? I'm tossing this coin every day. The coin is really biased towards heads, say. What is the probability that my guess is tails after tossing it t times? Right? So this is the probability that my action at time t is different than the state. It's not the correct guess. Yeah? So it turns out that the probability that I'm wrong decays exponentially with some rate r. And there's going to be a lower order term here. Again, it's hard to calculate these probabilities exactly, but what is easy to calculate is this rate r. And in fact, it does look like this lower order term is going to be logarithmic in t, so this is a small correction. Once you move ahead in time a little bit, it really decays very, very nicely like an exponential, the probability that you make a mistake. This r is something that we can calculate. Because we can calculate it and reason about it and prove things about it, this is what we're going to be focusing on. We're going to ask, what is going to be the speed of learning in this kind of setting? For a single agent, we know how to, if you tell me the coin is 51-49 or 49-51, I can calculate exactly what this r is going to be. It's going to be different if it's 51-49 versus 60-40, right? Then I'm going to learn much more quickly. Okay, so our object of study is going to be this rate of learning. Okay, let's look at a different model that's very easy. I'm going to change things a little bit. I'm going to have some number of agents now, but imagine that they do share the outcome of their experiment. So I not only see Omer's presentation and his conclusion, I get to see all the data of his experiments. So this is different than the model I've presented so far, just as a baseline to try to get a feeling for things. Now, everybody sees everybody's coin tosses, the actual experimental results. Well, that's the same thing as just speeding up time by a factor of n, right? Because now, I don't really care about your guess. We're all going to have the same guess. We're all going to choose the same action because we have the same information. But we're getting n coin tosses at each time period rather than one. So what's going to happen, the probability that I'm wrong is just going to decay with a rate that's n times the rate of a single person, because we've just sped up time by a factor of n. Does this make sense? Okay. Okay, so now let's go back to what we're studying, which is two people who do not see each other's data, but just each other's actions. Okay, so we have two people. Every person sees their own signal and the other person's actions. So now the probability that any one of these people makes a mistake, it's still going to decay exponentially, but it's going to have some different rate. And the question is, what is this rate going to be? So here's something very simple we can say. This rate R2, so the 2 here is because we have two people, is going to be somewhere between R and 2R. Why is that? Well, because I'm optimizing, I'm really, whenever I make a choice, I'm trying to minimize this. Now, I could always ignore whatever information I'm getting from other people and go with my own signal. That's just going to increase my probability of making a mistake if I ignore some information. So my probability of making a mistake has to be lower in this case than when I was on my own, which translates to me learning faster than I would on my own. So that's why this rate R2 for two people has to be at least R. On the other hand, if I also knew the other person's signals, I would just learn twice as fast as I would on my own. But I don't get all that information. I get some function of that information. I just see the action. So the fastest I could possibly learn is if somehow, in some sense, the other person's actions reveal their signals to me, or enough of the information of the signals to get the same speed as if everything was public. So we know that it's going to be somewhere between R and 2R. The question is, what happens? So in this process, when we observe each other, is it the same speed as if we were on our own? Or maybe information is perfectly passed just by observing other people's actions. And it's the same thing as if information was public. Yes?
I'm sorry, what's the private information? I don't need any private information in this example.
So when I say private, so let's go with this coin example. I have a lab where I'm tossing this coin every day. That's my private information. My public information is this action that I'm taking, the product that I'm putting in the market, whether I'm posting on Instagram. It's my guess of whether the coin is biased this way or that way. Which hypothesis do I believe in more?
So the action is not the heads or tails.
The action is also heads or tails.
So I'm not observing heads or tails from other people.
Yeah, it's a bit confusing because both the signals and the actions are heads or tails. But I have my raw lab data, which is all these coin tosses that I had. That's not revealed to the other person. What's revealed in each period is just the aggregation of everything that I know, which results in, given everything that I know, my best guess now is heads. Okay, so the other lab is doing experiments, whether to go with technology A or technology B. You don't know. That would be their own private information, their signal. You don't know, they're doing experiments on the metals, on whatever. What you see in the end is whether the product they put on the market uses technology A or technology B. That's what's public here. Okay? Now the question is, when I just see the other lab's final decision, well, every day, does that basically reveal to me all their private information in the sense that we learn at the same speed as we would have if I saw their information? Or maybe that basically reveals nothing to me. And I learn just as fast as I would on my own. Yeah.
So going back to the restaurant example, so one reason why I could choose to go to a restaurant where everyone is going could just be like social proof or something like that.
I'm a mathematician, so I don't care about other people.
So you're saying that mathematically it doesn't really matter? Because
it's an assumption of the model. The assumption of the model is every day I just ask myself, is it more likely that this choice is better or that is better in terms of, is the state high, is the food here better, is the food here? And I just go with that. I don't care about which restaurant other people are going to, except that reveals to me something about their own information.
Right. I'm just saying that the reason why I might choose something might not be because I think the food is better. I might think the food is actually better here, but I might still go here because everybody's going there and it's sort of socially awkward to go here, And so I'm saying,
No, good. So this would be a really interesting paper to also write. I don't know that people have done this particular variant in this kind of setting, but you could imagine that if you have that kind of motivation, things would get much worse, right? Because if the first few people went to restaurant A, the rest of them would just go there, even if they had very strong signals telling them that that's the wrong answer, right?
That stuff happens in human behavior all the time, right? We do
Yes.
things because other people do it,
Yes.
even though it's suboptimal.
Right. So the thing is, if you wrote a paper which says, I don't really care. The first person who comes there looks at their signals and makes the decision. Everybody else just follows the first person. That wouldn't be as interesting as saying everybody else is trying to do the best they can. They don't care about being with other people, and still it fails. Still a herd forms, right? So that was the point of these original papers, that you don't need a particular desire to form a herd. You get the herd just out of optimizing and trying to make the best choice. Yeah? Yes?
So one, I understand that like the action is an aggregation of an agent's all private observations. And now I think like the number of the private observations is related to confidence. Like it's like if I observe your action and I know that your action is a result of 100 private experiments, then like your action is much more informative of the actual like state of the coin. But I think like in your model, somewhere you said like everybody only has like one private observation.
No, you get one at every period. So what happens in each period, I do a new experiment, I get a signal. You do your own experiment, you get a signal. Then you take an action, I take an action, and we see each other's actions. And then we do this again and again and again.
But I know that your action is only a result of like doing one more experiment.
No, it's also a result of looking at your action from the previous periods.
Oh, do I know the length of my history and your history?
Yes.
And at each time step, you only do one experiment, and I only do one experiment.
Correct.
And I also know the length.
Yes.
So I know how many experiments, private experiments you have done.
Yes.
So I know that confidence weighting.
Yes. But you also know that my actions have been influenced by your actions. So when you see me, imagine that in the second, maybe we did different things in the first period. Maybe the first period, we each did one experiment, we just go with that. In the second period, I have a new experiment that I did, but I also saw what you did in the first period.
But is it a deterministic decision based on these two inputs? Or
Yes, the decision is exactly, I do the best given all the information I have.
So it's deterministic, so you can trace back all the possible observations that the person saw, and you have all the data.
Well, no, because it could be that many different experimental outcomes result in the same action. So maybe, okay, let me give you a scenario this is important. So imagine that in the first period, I get a heads. I mean, my experiment shows me, go to, it's a head. So I say my guess is heads. You also get a heads. You say, okay. So now, what information do I have? You actually reveal to me your experiment and what you did, and I have my own experiment. Now, in the second period, you do another experiment. I don't know what it is, but I can see your action. Maybe it's the same action again.
But you know the relative weighting between my decision based on your previous action and my own flip of the coin. So you can undo this and
well, no,
reconstruct.
not
Well,
exactly,
no.
because imagine that the first
Okay.
few experiments that we did all in
binary. Okay,
sorry,
okay.
maybe if other I'll explain this because it's important. So imagine that the first few experiments that we both do give information in the same direction. They all tell us to choose technology A. So we choose technology A in the first few periods. Now imagine that after we did that for the first 10 periods. In period 11, suddenly I got a signal in the other direction. I'm not going to change my choice. I'm still going to go with technology A because I got 10 signals going for technology A. I see you going with technology A this whole time. The fact that I got one signal in the other direction is not going to change what I do. So I still go with technology A. You cannot see that I got a signal going in the other direction. And you maybe also got a signal in the other direction, but you stick with technology A. Okay? So there's a lot of information lost when you only see somebody else's actions versus seeing their actual signals. Yeah? Does that make sense? Okay. Good. So the question for two people is, how quickly do we learn when there's just two people? And the honest answer is that I don't know. In fact, it could be this, it could be this, it could be anywhere in between. Where I can say something is what happens when we have many agents. So now we're going to have n agents. So it's not just, it's each one of us does this experiment. Or a lot of companies trying to decide between technology A and technology B. We each have our lab. We each put out a product every cycle, and we see what products other people put out. Now again, there's going to be some rate of learning Rn, and for the same reasons as before, it's going to be somewhere between R and n times R. The slowest we can learn is just the same rate as we did on our own. The fastest is n times as fast, when n is the number of people. So what happens here is something that we call this Bayesian groupthink, and it's really related to this example that I gave before. So imagine that each signal that we have in each time period is kind of weak. And it could be that there's 7 of us, and it just so happened in the first period, most of us got a signal in the wrong direction. It happens, either just 51, 40, 49 coins. So what happens? In the second period, we're all going to go with the wrong thing. We're going to go with technology B, even though technology A is better. Now, what's going to happen in the period after that? I see everybody going with technology A. Even if I have my own little weak signal towards technology B, I'm going to still stick to A. And everybody else is doing that too. So that gets me even more convinced that technology A is better. And we get trapped into this thing where this lasts for a very, very long time. It's not going to last forever. Eventually, somebody will get enough signal to break out of this. But it lasts for so long that it really caps our rate of learning. So it turns out that if you fix your private signal distribution, say there are these 51, 49 signals, there's going to be some cap so that the rate Rn is strictly less than some constant times R, no matter how big n is. So if, for example, if C is 4, then no matter how many people we have, we're never going to learn more quickly than 4 people. Almost, there's 100 people there, but the rate is only as fast as sharing 4 streams of information. There's 4 people revealing everything to each other. So the conclusion from this is, in the end, that almost all information is lost when the group is large. Yeah.
If you were the only agent able to see the others, so everyone else is just doing majority vote of their own coins, and you're the only one, you can see your coins and you can see the majority. So you can do, if you want, majority of majorities or whatever the heck you want. Does that, I would imagine that might actually be better than the agents actually adapt.
Yes, then the rate would increase linearly with a number of agents. But here it's capped.
So the fact that the agents
see each other
is making it worse.
Making it worse, yes. We get trapped in this thing where I'm sort of relying on yours, you're relying on mine, and there's very little exchange of information.
What's the optimal n?
No, it's gonna, well, okay, we don't even know that it's increasing with n, but all we know is that it might be increasing with n, but it's also capped. So it's not gonna go above some bound. It makes sense that it's increasing. You have more people, things go faster, but in the end it's gonna hit some cap. Yeah.
So at every step, like, there is a weighting that decides how much I trust my private experiment and how much I trust my observation of like other agents' actions. And then like, do you put assumptions on like how individual specific that trust distribution?
Okay, so this is a subtle point, but we don't have any weights. We just do the Bayesian calculation. So there's a probability space. There are all these outcomes. You know exactly what rule I'm using. It's defined recursively by I'm doing the optimal thing. Now you can condition on that and ask, given this information that I have, what is the probability that this is better than this? So you don't actually need to specify any heuristic or any algorithm. The algorithm is given by maximizing the probability that you're right.
So like without any like this trust thing. Oh, okay. And then like that's why the like R2 is between R and 2R.
Yes.
Okay. Thanks.
Yeah.
How does C depend on the accuracy of private information? So 4060 versus 4159 versus 2.5 versus 49.
So this we can calculate. It turns out that the C is bounded. So it's going to be between, I forget, something and something. In the end, it's never going to be better than some number of people, regardless of how strong the coin is. And you can imagine more complicated. Maybe I get a Gaussian signal. For Gaussian signals, right? So when I do an experiment, my experiment is, we don't know what the weight of these quarters are. All the quarters have the same weight. We don't know what the weight is. What do? We put them on a scale. The scale gives us a Gaussian measurement around the real mass. So this is our signal every time. For Gaussian, C is 4, exactly. So that's something that you can just calculate. You never do better than 4 people, even if you're 15 people.
And it doesn't matter what the relative probability is between the
No.
and failed?
No. So that's an interesting thing. In general, these rates are, okay, this is not moving. But these rates, these exponential rates, everything like the initial probabilities get swallowed in the lower order terms. These are very robust to the parameters of the model. Also, it's robust to say, okay, a priori, maybe the probability that the state is this or that is not half-half. That does not change R. You can also imagine that my threshold for when I switch, what belief do I need to have to switch between doing this and doing that, is not 1/2. That's also robust here. So what my rule was, if I think the probability of this state is bigger than 1/2, then I do that. Otherwise, I do this. But imagine that I'm worried about type 1 errors much more than about type 2 errors. So I need a 0.9 threshold to switch between this and that. It all gets swallowed in the lower order terms and doesn't change the rates. Yeah.
So here, I mean, the network is this complete directive of how the information is flowing.
Yes.
And is it possible to say something like if there's some structure, like maybe no small directed cycles or something, then it flows better?
Okay, excellent question. Imagine that we have a network. People are not able to observe everybody. It is strongly connected, so there is a path from every person to every person. You get the same kind of results. So this is a different paper, but you get the same kind of result.
Omer?
Yeah.
I just wanted to make sure that you have another point to make.
No,
Or you're done? That you
no,
make it?
I'm done.
Or you're done?
I'm done. I wasn't even going to go to this, but I felt obliged.
Okay, in that case, I think Paul had.
Oh, sure. I was going to ask it. So this feels like a kind of tragedy of the commons case where each person is so selfishly trying to look over their shoulder that they, for the sake of selfishness, they pollute the common information streams that collectively trying to be selfish.
Yes, so I also have a slide for that. You can ask, okay, everybody's optimizing, information gets lost. Maybe we could tell people what to do and increase the rate. We don't have an algorithm for that. We don't have a proof that anything can actually increase the rate, but we do have simulation results. And our intuition is that there should be something that helps increase the rate, which you make people a little bit cocky, a little bit overconfident in their own results. So imagine that my coin is 51, my experiment gives me 51.49, and so does everybody else's, but I think that everybody else's is much weaker. Everybody else's is 0.5001, and mine are really good. What's that going to do is I'm going to be less affected by other people's actions. When I do this Bayesian calculation, I'm not going to be so impressed when other people are doing something different than me, which will make me rely more on my own signals, and in the process will make me reveal more of my private information to people. So in simulations, it looks like that actually helps. But these are all asymptotic statements, and we can't really, yeah.
So I was just thinking, so in reality, what often happens
What's that word? I'm not sure.
is that we might not actually be able to do our own experiments as often as we can observe, right? And so it might be hard for us to get our own data, and it might be easier to see what other people are doing. And so that's one reason why something like this might have been adaptive in the first place, is where you can use what other people are doing as a quick shortcut to figure out what's best, because you might not be able to sample all the restaurants and do your own experiments.
Right.
And so I was just thinking, in terms of why something like this might work, if it leads to suboptimal solutions.
I see. I mean, in the end, evolution, I don't know much about evolution, but if I'm just trying to maximize my own chance of surviving or breeding or whatever, I would do this, right? So you would need to have some kind of evolutionary force that helps the entire species at the expense of individuals, some kind of altruism developed in evolution to not have this.
No, even if you're completely selfish, if you want to maximize your own survival.
If you don't have information, you do what other people are doing. Sure.
All right, and like his self-reporting, Omer is actually a very social mathematician, and so he will be available at the coffee for further discussion. Let's take half an hour. We'll be back at 11:15. Thank you.